Welcome to day 20 of the Intuitive Calculus course. Today we're going to introduce the concept of definite intervals. Until now we learned about indefinite intervals and we learned a lot of techniques for calculating these types of intervals. And now we're going to see why all of those techniques are useful and why it is useful to know how to calculate intervals, especially when we learn about the fundamental theorem of calculus. Now we're going to introduce this concept of definite interval that it is a very interesting concept because it generalizes the concept of area, that we know from basic geometry. So we're going to begin with a physical intuition of this idea. Just as with the derivative, there is a physical interpretation of this idea, and we're going to see how it is connected to the idea of area. So let's say that we're going to consider a particle that is moving, and let's say that the distance traveled by this particle is given by a function. It is given by this function. S of t equals t squared over 2. S of t gives the distance traveled by the particle until time t, and it is given by this function. The graph of this function is a parabola like this one. So now we have distance traveled, and if we take the derivative of this function, we get s prime of t, and that will be t, because s of t equals c squared over 2. So now this is another function of time that if we graph, we'll get a straight line like this one. And if you remember what is the physical interpretation of the derivative, it is just velocity. This function gives you the velocity of the particle at time t. So this is the graph of velocity. That's why we have the letter v here on the vertical axis. So now let's say that we want to solve the following problem. Let's say that we have given velocity, we know the velocity of the particle, and we want to calculate the distance traveled over a period of time. So we're going to begin to solve this problem within a very small time interval. We're going to take a small interval here in the t-axis, the horizontal axis, very small interval that we're going to call dt. In fact, this interval should be very small. Here I draw it not very small, but you should imagine it as very small. And we're going to take the value of the interval, the value of the function on the interval, and if we take the interval very small, we're going to see that we can consider the function constant on this interval because we are taking the interval very small. So we're going to say that the function velocity is constant in this very small interval. This is an approximation to reality. Now, if you consider that velocity is constant in this little interval, it is easy to calculate the distance traveled, because distance, we know from physics that distance is velocity times time. Velocity times time. So we're going to call this distance, we're going to call it ds, and we're going to say that velocity is constant in this interval, and we're going to say that equals v, and we multiply it by dt, that is the interval, the width of the interval that we took. So we get this equals v dt. But what is v dt? V is the height of this rectangle here, and dt is the base. So v dt gives you the area of this rectangle. This is v dt, the pink area here. So the idea here is that, well, this was an approximation. The area of this rectangle is an approximation to the real distance traveled. So the real distance traveled will be just the area below the curve. Will be the area between the line that gives you the velocity and the x-axis. That would be the velocity. Now let's say, what if we want to find the distance traveled during a longer time interval, not necessarily a very small time interval. Let's say that we want to find the distance traveled between time 0, that is this point, and another time t0 here. We want to find the distance traveled. And we see that the distance traveled will be the area below this curve, from 0 to t0. And how can we, well, in this case it could be easy because it will be just the area of this triangle. But if you have another strange curve that goes from here to here, how would you calculate the area below this curve? And the idea here is to simplify the problem by simplifying it to the problem we just solved. We're going to take rectangles like this one from time 0 to the time we're interested in, like this. We take many small rectangles like this, and we know how to calculate the areas of each of these rectangles. So we're going to do that. We calculate the areas of these rectangles and we add them up to get the area below this curve. And we see that this is an approximation. The width of each of these rectangles is dt. And how can we improve this approximation? And you may guess already that we're going to increase the number of rectangles like this. We increase the number of rectangles even more, and you see that we get a better and better approximation to the area below this curve. And the fact is that we're going to take the limit, because we're in calculus. We're going to take the limit as the number of rectangles approach infinity, and the sum of the areas approach the area below the curve, and the area below the curve is the distance traveled. So here you can see I just wanted to show you the intuitive idea. We're not here defining anything. I just wanted to show you how this concept of area below a curve is related to the physical concept of distance and velocity and those physical concepts. So in the next videos we're going to define things more precisely. I'm going to see more examples of this concept. So that's all for now. Thank you for watching and see you next time.